This module described the concepts behind the use of carriers and tracers and how they are used to monitor radiochemical processes. At the end of this tutorial, you will be able to describe how carriers, tracers, and yield calculations are used in radiochemical analyses. Calculate the activity of a radionuclide based on chemical yield. Calculate the activity of a radionuclide based on radiochemical yield. List the sequence of steps that should be followed during an analytical protocol that incorporates yield monitors. The key concepts that will be emphasized in this module are: yield monitors must be added before the first chemical separation step. The differences between carriers and tracers. The differences between isotopic carriers versus non-isotopic carriers. Tracers can only be used as yield monitors and not as carriers. And important chemical assumptions when using yield monitors. Why use tracers and carriers? In our introductory module, we discussed that the mass concentration of radionuclides that may be found in drinking water samples is very, very small. For example, 5 picocuries per liter of radium-226 is the maximum contaminant level, and its mass concentration is 5.1 times 10 to the minus 10th ppm. Compared to any other chemical component of the solution, this is a minuscule mass of material. Even when performing gravimetric analysis of major sample contaminants, there are some losses during the sample processing. But the losses are small compared to the total mass present. When radiochemical separations are performed, there are many ways the radionuclide of interest can be lost during the process. These losses must be accounted for. The key concept here is that tracers or carriers are added to the water sample at the beginning of the analytical method, prior to any chemical or physical separations having been performed on the sample. These carriers or tracers serve as a means to determine what fraction of the analyte is lost during the analytical separation process. Losses of radionuclides during the analytical separation processes are due to irreversible adherence to dust, container walls, ion exchange resins, and filters. Every surface that the solution comes into contact with has many sites where ionic materials can hide. If we add a material that is chemically identical to the radionuclide of interest, it will also occupy these sites. However, we will know exactly how much of this chemically identical material is added. Thus, if we can measure how much is left at the end of the analytical process, we can get a fractional yield. Since the chemically identical material and the radionuclide of interest are the same, the yield for the radionuclide is the same as that of the chemically identical material. The term applied to this chemically identical material is carrier. That's because it carries the small mass of the radionuclide along with the bulk mass of the chemically identical material. A carrier is generally determined by a standard analytical technique such as gravimetry, titrimetry, or spectrometry. The key concept here is that carriers are chemically identical materials to the radionuclide of interest that have a significant non-radioactive mass. For more details on carriers, see the reference materials cited on the slide. The figure on this slide depicts what can happen when there are very few atoms available and a surface that is unsaturated with respect to that analyte. Although the number of sites that are available for atoms to hide out may be small, When we are dealing with radionuclides, in this case strontium-90, there are very few atoms. Thus, most of the analyte is irreversibly adsorbed onto the surface. If we don't know how many sites there are, or how many atoms there are originally, there is no way to account for this loss. If we have the same amount of surface area for atoms to hide out as in the previous example, and we have added lots of atoms of the analyte that are non-radioactive, stable strontium, the mass of material adsorbed onto the surface reaches a maximum. The surface becomes saturated mainly with stable strontium atoms because of the vast mass of excess above the radioactive atoms. If the atoms are all chemically identical, the radioactive and non-radioactive analyte are in the same proportion on the debris as they are in the solution. If we measure how much non-radioactive material is left not adsorbed on the debris and determine the fraction that we originally put into the sample, this is the yield. The key concepts associated with carriers are there are two different types, isotopic and non-isotopic. The isotopic carrier is a stable isotope of the radionuclide of interest. For strontium-90, stable strontium is added to the sample at the beginning of the sample analysis. Radioactive and stable strontium are chemically identical. If the stable strontium precipitates as the carbonate, the radioactive strontium will precipitate as the carbonate as well, because the total mass of strontium present will exceed the solubility product constant for strontium carbonate. Another example of an isotopic carrier is barium, used for ensuring that barium-140 is effectively removed from strontium-90. This is an important application when fresh fission products may be present in the sample. The barium is precipitated as the chromate from slightly basic solution, while strontium remains soluble. In this application, where both radioactive strontium and barium are present, the carriers for each are added at the beginning of the analysis. An example of non-isotopic carrier is when barium is used in radium analysis. Since radium has no stable isotopes, a chemical homologue is used. Barium and radium are both in group 2 in the periodic table and have very similar chemical properties. When barium is added as a non-isotopic carrier and precipitates as the sulfate, radium will co-precipitate with the barium. Co-precipitation means that the radioactive element precipitating would not have a high enough mass concentration to precipitate if the non-isotopic carrier were absent. Another example of a non-isotopic carrier shown on this slide is the use of stable yttrium to carium actinium-228. Actinium has no stable isotopes. Actinium and yttrium are chemical homologues, and both will precipitate as the carbonate from basic solution. In this application, the actinium-228 is allowed to grow into freshly isolated radium-228. The difference here is that the yttrium carrier is only added after the radium-228 has been isolated and we are ready to precipitate the actinium. This technique of delaying the addition of the non-isotopic carrier is also commonly performed in analysis of the transuranics. The table displayed here shows many different non-radioactive carriers that are used for radioactive elements. You should be easily able to distinguish the isotopic from the non-isotopic carriers. Are you ready for a small challenge? Described on the left is the process used to perform the separation of strontium from a sample. Included are the salient pieces of information that you need to calculate the following. First, the chemical yield, and second, the amount of strontium-90 present in the sample in picocuries per liter. Try the calculations, then go to the next slide to check your answers. The chemical yield is calculated as a fraction. Note that you needed to use the gravimetric factor for the amount of strontium carbonate produced per mass of strontium ion added. The value of 0.7789, carrying all 4 significant digits, should be used in subsequent calculations. Rounding to 3 significant figures should only be used in the final expression for the activity. The final value for strontium-90 concentration is 5.76 picocuries per liter. If you did not get this value, please review slides 3 through 10 before proceeding. In many of the radiochemical methods, a chemical is added with the express purpose of tying up a radionuclide so that it will not participate in certain chemical reactions. Such chemicals are referred to as holdback or masking agents. When a chemical specifically prevents a radionuclide from being precipitated or extracted, it is referred to as a holdback agent. When a chemical added to the analysis process changes the ionic character of the radionuclide, it is said to be a masking agent. Stable strontium performs this function when yttrium is precipitated in basic solution to isolate yttrium-90. The stable strontium minimizes any strontium-90 that will precipitate with the yttrium by occupying sites on the yttrium hydroxide precipitate that strontium-90 might otherwise occupy. A masking agent is a chemical that changes the ionic characteristic of the radionuclide. When acetic acid is added in radium-226 analysis while precipitating barium sulfate, the acetate ion buffers the pH so that the radioactive lead present will remain complexed with the EDTA as a negative ion. The barium and radium at that buffered pH have very small complex formation constants with EDTA and easily precipitate as the sulfate. The lead is said to be masked by the EDTA. Tracers allow the determination of chemical yield when stable carriers are not available, as with the transuranics. The tracer must have certain characteristics in order to successfully allow the determination of yield. First, the tracer must have a long enough half-life so that it does not decay away during the analytical process. Second, it cannot be possible that the tracer would appear in the sample in question. For example, in uranium analysis, uranium-232 is used as a tracer for environmental water samples, as uranium-232 is not naturally occurring. Third, it should have the same chemical characteristics as the radionuclide being determined. Ideally, it would be a different isotope of the same element, as in the case of U-232 we just noted. As with carriers, the tracer must be added to the sample at the start of the chemical method to ensure that isotopic equilibrium between the radionuclide and the tracer is achieved prior to any separations being performed. Some other characteristics of tracers are noted on this slide. It is very important that the tracer not interfere with the radiometric determination of the radionuclide being determined. For example, if a potential tracer had the same alpha particle energy as the radionuclide of interest, it could not be used. Tracers are also considered to be massless. As we showed in Module 1, the mass of radionuclides is very small. Thus, tracers don't do anything to minimize losses on surfaces used during the analytical method. As we noted earlier, the tracer must have a long enough half-life so that it does not decay to any significant degree during the analytical process. Also important is that it should be able to be easily purified by a standards provider so that other interfering radionuclides are not present. We know that many of the radionuclides that we use or determine have radioactive progeny. A good tracer will have minimum ingrowth of its progeny, and the progeny will not interfere with the analytical method. The tracer should be readily available and be in a chemical form that is easily transformed during our analytical process, ensuring that isotopic exchange with our radionuclide of interest is ensured. Analysis for plutonium-239 and plutonium-240 is performed using either a plutonium-236 or a plutonium-242 tracer. Both these isotopes of plutonium work well since they do not occur as normal products of nuclear reactions, and they both have alpha ray peaks that are easily resolvable from the plutonium-239 and plutonium-240 alpha peaks. The spectrum shown on this slide shows the plutonium-239 and plutonium-240 peaks that overlap. This problem will be discussed in Module 4.3 in more detail. And also, it is resolvable from the added tracer, plutonium-242. Note that these peaks are well resolved from each other. The table on this slide shows some of the more commonly used tracers in radiochemical analysis of drinking water samples. In the case of strontium-85, it decays by a different mode and is determined by a separate gamma ray analysis technique. For analysis of curium-244, an americium-243 tracer is used, as no suitable sources for curium tracers are readily available. The data provided on this slide is sufficient for calculating the activity of uranium-235 in a sample. Because the half-lives of uranium-235 and uranium-232 are so long, it can be assumed that no correction for decay is needed. Calculate the activity of the uranium-235, then check your answer on the next slide. The first step is to determine the radiochemical yield based on the uranium-232 activity determined. You should have calculated 0.75. Remember, yield is a dimensionless quantity. The final activity of the U-235 is 1.95 picocuries per liter. Tracers are massless materials. Thus, when there is no carrier present, losses are controlled only by the analyst's technique and the cleanliness of the surfaces that the sample comes into contact with. Radiocolloidal particles can form due to the low concentration of these radioactive materials. Radiocolloids are not filterable, ion exchangeable on a resin, or extractable into a solvent. The methods are designed to minimize this problem. One of the important considerations to prevent radiocolloid formation is the time that the radionuclides are allowed to remain in solution without being in a final counting form. This should be minimized. The table on this slide is a review of what we have already discussed about chemical and radiochemical yield. Another term is introduced here that we have not yet discussed. That is recovery. Recovery refers to a quality control parameter related to the laboratory control sample, LCS, or matrix spike sample, MS. Recovery is how much of the radionuclide under investigation originally added in the LCS or MS was determined or recovered at the end of the analysis. Thus, the main difference between yield and recovery is that yield is determined based on a stable carrier or a tracer, and recovery is based upon the amount of radionuclide of interest recovered after it was intentionally added to a sample. The general steps that are taken for the addition of tracers or carriers during the analytical method are shown here and on the next slide. The critical step is the very first one. When adding a tracer or carrier to determine chemical yield, a precise amount of the material must be added at the very beginning of the method before any chemical separations are performed. Next, the sample must be treated chemically to ensure that all atoms of the radionuclide, tracer, and carrier are in the same chemical form and oxidation state before proceeding with any chemical separations. This process is known as isotopic exchange. Since the yield monitor acts chemically the same as the radionuclide of interest, the yield monitor will reflect the amount of radionuclide lost during the chemical processing steps. The fractional amount calculated, that is, the amount found divided by the amount added, is in the activity equation as a factor in the denominator. Separate measurements must be made for the radionuclide of interest and the yield monitor. These measurements can sometimes be made simultaneously, as with two alpha emitters, or by different techniques, weighing the mass of barium sulfate precipitate. The yield is determined by comparing the final quantity of the measured yield monitor to the original amount of that monitor added. This results in a fraction that has no units. The yield is then used to perform the final calculation on the activity of radionuclide in the samples. Remember, since isotopic exchanged at the beginning of the method, any losses of radionuclide are reflected in the yield of the tracer. The yield corrects for these losses. The principal assumptions we make regarding yield materials are: the concentration of the yield carrier or tracer in the initial sample is 0. The yield monitor does not interfere with the measurement method. The measurement of the yield monitor is quantitative and accurate. If we are not assured of these three requirements, the analytical results may be biased. How could you account for the presence of native barium in a water sample if we're using barium sulfate as a yield monitor? One way is to measure a separate aliquant of the water sample for barium content and factor this into the barium mass added for yield determination. Now that we have completed this module, you should be able to define what a carrier is, what a tracer is, how to measure yield, the difference between yield and recovery, and calculate the activity of a radionuclide when a tracer or carrier is used. You should also be able to discuss the properties of a good tracer or carrier and the basic assumptions that must be true for them to be effective yield monitors.